You are audible.
electronically tunable, flexible, transparent. We talk about electronically tunable and flexible, right? And in addition, they can be made transparent. So this is newer than those I described last time. Um, that has PDMS. The problem with the uh, flexible conductive material is they are not fully transparent. Um, but so when you use them like those flexible antennas you saw, uh, they they are not totally opaque but not fully transparent. So this another way to do it is use some material, conducting material that is fully transparent. One choice is just water or any liquid that is conducting. So in these flexible transparent antennas, to make the ground plane, we just use water. Of course, water is not solid, and although it is flexible, so you have to contain it somehow. So we put it inside a PDMS container, like I explained last time. So the ground plane is a water contained in a PDMS container, which can be fabricated in the same way other antennas I described last time. And then there may be some conducting strips that are not fully transparent and the reactor diodes, etc. So that is another way of making these antennas flexible, um, reconfigurable, wearable, and also transparent. So you can, it will not uh, disturb the nature of what you're wearing. So you can see some of them. They were done when I was in the previous university, Macquarie University. Um, you can see the PDMS blocks with water inside. Um, Here they're looking at Macquarie University logo through the antenna, through the ground plane, and totally transparent. I mean, the antenna is also very, very transparent. Only the connector is visible, right? So that's the fabricated antenna, and it's flexible as we're doing those tests. To make it uh, waterproof, again, we embedded all the conducting parts and connectors and all that, except the external connector, the other parts inside PDMS. I'm back. So because of limited time, I think I will I'll just show one more related to what we discussed last time. The ultra band monopoles, right? Remember we discussed ultra wideband monopole with two hemispherical slots, and this is a spherical. Sorry, not really spherical. It's a circular. Sorry, last time we looked at two hemicircular, semicircular slots, but this one is not a slot. This is circular conductor, and feed line and the ground plane. That is very common ultra-wideband monopole antenna. The difference here is to get higher directivity. So this part is a standard ultra-wideband monopole antenna. To increase directivity, put it inside a TEM horn. We cut this side of the horn to avoid shorting, and left the horn. This is kind of a short horn. Um, if you search literature, you can find that I published quite a few short horn or quasi-TM horn papers with Professor Anand Verma of University of Delhi, South Campus. So this is also another joint paper with him and Yogesh Ranga I mentioned last time. And so this approach gives more directivity than just the printed monopole, but it's taller. The side walls can also be printed, but it's taller. And I will explain later today. There's another method to increase the directivity of these antennas by using reflectors, ultra wideband reflectors. That's the prototype. I should have some slides of this, but I can't find among my massive collection of slides. Yeah, that's, I think FR4, the down plane is on the other side, radiating monopole on this side. Very wide band. You can see this is the measured input reflection coefficient. Not always less than -10, but it's less than -10 or very, very wide. Sometimes it went a little bit up above -10. That means return loss less than -10 dB at some frequencies, but it's pretty good. Even simulations, theoretically, we expected some issues. Otherwise, the bandwidth, as you can see, some measured bandwidth from about even less than 3 gigahertz to way up 18 plus gigahertz. It's a very wide band antenna, even wider than the necessary UWB bandwidth of 3.1 to 10.6. In fact, another PhD student actually designed antennas like this with massive bandwidths, 1 to 25 ratio bandwidth. Those are published, so you can find them. I don't have them here in my collection. I mean, in the lecture material. Okay, let's move on. We can come to this later. So I keep checking the plan because we're supposed to discuss other surfaces today. Okay, let's go to what inspired us. Yeah, that's a good place to start. The electromagnetic surfaces. And so the current metasurface research and a lot of past research, as you see, they're not just antennas, there are a lot of surfaces associated with these antennas. And some of them are not really thin surfaces, they are bigger materials like metamaterials, electromagnetic band gap structures. A lot of these are periodic structures or part of a periodic structure, periodic in one dimension, 2 dimensions, or 3 dimensions. So our research, no, not our research, others' research on electromagnetic band gap, also known as photonic band gap. People in optics call it photonic band gap. Microwave antenna people call it electromagnetic band gap. It's the same thing. Photonic crystals, so they call photonic crystals, we call them electromagnetic band gap structures. Then metamaterials, metasurfaces. There's a lot of research on these periodic electromagnetic structures. That inspired our research and innovations, because a lot of theories have been revised, built, expanded, extended on periodic structures, and we can use them to design better surfaces and integrate them with antennas. Some of the structures, as you will see, not totally periodic, some are aperiodic, but inspired by periodic structures. So these are some of the examples. You can see this is, I will describe this later. This is an ultra-wideband antenna on the top, and this is a reflector, ultra-wideband reflector. And you can see that at least the top of that reflector is a periodic in 2 dimensions. This is electromagnetic band gap structure in a wood pile configuration, and that's a periodic structure, periodic in 3D, that has 3D band gap, electromagnetic band gap. This is another one, a 2D printed planar structure, as you see, and in fact it is artificial magnetic conductor operating in 2 bands, dual band artificial magnetic conductor. This is another one. This is frequency selective surface. It's a dual layer frequency selective surface, but it has a very it has a unique property. Now you can design frequency selective surfaces, FSS, to behave like a filter. You can design it to block like a band reject filter, to block the transmission of specific band and allowing other bands to go through. For example, if you use one of these if you don't want your Wi-Fi signal to go out of your building, you can have a reflector, FSS, that has good transmission at other frequencies, like mobile frequencies. So you still get the mobile signal through the FSS. Your mobile communication phone would not be affected. But for example, you're using 5 gigahertz Wi-Fi, your Wi-Fi signal will be blocked by the FSS, so it will not go outside your room for security purposes, so physical security. But normally these are done by frequency selective surfaces that transmit other frequencies and reject the band you want, for example, Wi-Fi band, by reflecting. So instead of transmitting, it reflects. So we call them transmit reflect type of frequency selective surfaces. But in Wi-Fi, in the communication environment, that can create problems. Too many reflections create delay in reflection delay due to path delay, and that can affect your Wi-Fi performance from telecom perspective. So what we have done here is we actually designed this so that it behaves outside the band. It behaves like a normal FSS. That means it transmits other signals below 5 gigahertz and above 5 gigahertz. In the rejection band of 5 gigahertz, instead of reflecting, it absorbs your Wi-Fi signal. So it's a lossy FSS. It absorbs Wi-Fi band and transmits other band. So we call them transmit absorb frequency selective surface. Just to give an example, we will look into those in more detail. And so now I switch to actually I can keep going on this. So this is that more about that absorb transmit frequency selective surface. We published this in IEEE transactions on antennas and propagation, capable of absorbing as opposed to reflecting the 5 to 6 gigahertz Wi-Fi wireless local area network signals while passing mobile signals. So all sub-Wi-Fi bands, those days there was no mobile in this range. I think even now there's no mobile in this range, in the Wi-Fi band. The normal handset mobile broadband signals 700 megahertz, 900 megahertz, by 1.2, 2 gigahertz, etc., would pass through the surface. They are not blocked, they are not reflected. But the Wi-Fi signals are absorbed. The absorption reduces additional multipath, delay spread, and resulting fading. It's called delay spread fading caused by reflections. This is fairly common, well explained in telecom theories, how the multipaths and delay spread affects throughput in a telecom system. When you have reflections, when you have too many reflections, so we avoid reflection by absorbing. Sometimes people think that, okay, absorbing is not good, it's better to reflect because absorption is lossy. But in some cases, it's good to absorb rather than reflecting, creating a mess in the telecom system. So how did it work? It has two layers. Hard to see here. It has two layers, almost identical. You can see the two layers here. One with conducting cross dipole elements. So this is a conducting cross dipole element. So very standard FSS printed on a substrate. I think because FR4 is cheap and this is large, we printed it on FR4, standard conducting. But the second one is unique. The second one with resistive cross dipoles. So this material, the cross here, is not conducting, it's resistive. So these are the unit cells, right, in this 2D periodic structure. So what happens, how does it work when there's an incident wave incident on this in the Wi-Fi band? It's reflected by this reflecting cross and comes back, and it's absorbed by the conducting cross. Actually, in its way forward also, it's absorbed partially by this conducting cross. Resistive cross, not conducting, resistive cross, and other part goes there and reflected back. On the way back, that part is also absorbed by the resistive FS. So with this two-way absorption, you can get good absorption from the surface. The other frequencies 900, 1900, 1900 megas mobile bands, and it transmits good and performs well for all polarizations, not just vertical uh, and horizontal, the orthogonal, etc., and also for normal and oblique angles of incidence. Because the mobile signal is not always oblique, normal, it's oblique. Your 5 signal may incident at an angle. So let me see, I may have this paper open. Paper PDF open. Shielding. Give me a second. Let's got to go through my PDF collection. Planar Chakra shielding. FS is absorbed. Right. Yeah, I got it. So change. Stop presenting. Change to PDF. So this is the paper in IEEE transactions. Oblique. Now this is not the basic paper, the first paper. This is about oblique incidence performance of this. Actually, no. This is a different FSS. This is total absorb actually. That's absorb transfer. So this is the absorb transfer. This has all the details, dimensions of the patches and how we design. It's actually not in transactions, actually microwave and wireless component letters of the MTT society. So this is this plot is tells the story pretty much. This is for a conventional FSS, conventional reflect transmit type of FSS with a rejection band around 5.2 gigahertz. Okay,
Your voice is not coming, sir.
okay, let me start. So was it like that from the beginning when I switched this paper?
Your
And
voice was coming when you were switching to this paper. Now it is also coming.
okay, so this is the transmission and reflection of a conventional reflect transmit FSS. Okay, this curve is the transmission. You can see that it transmits high frequencies, low frequencies, but it rejects the 5 gigahertz 5.25, around 5.25 Wi-Fi. Very well. So the transmission is below minus 10 dB. Now, how does it reject? You can see the other curve, that is the reflection. There's high reflection in this band. So it's rejecting transmission by reflecting it back to you. Back to that Wi-Fi comes back to you, causing the issues I mentioned below, delay, spread, etc. So that's the conventional transmit reflect type FSS. And this is what happens when you put the resistive FSS layer in the absorb transmit surface. In the absorb transmit surface. And now the transmission has the same story, right? Around 5 gigahertz, 5.25 gigahertz, there's no transmission. It's a band reject filter. But if you look at the reflection, there's no increase of reflection in this band. The reflection is also low, reasonably low, and better than this, much better than that in this band. So it's not reflecting either. So what's happening to your energy? They absorbed by the resistive dipoles, the resistive material in the unit cell, in the resistive FSS. So together, when you look at the transmission and absorption, that's one side. On FR4, these are simulated. Transmission S21 is the solid curve, and reflection S11 magnitude is the dotted line. Okay. Now you can, if you want to absorb everything, right? Not just 5 gigahertz like a filter, but if you want to absorb everything, you can make absorber, thin printed absorber using the same method. So that is this that we published in IEEE Transactions on Antennas and Propagation as a communication, with only small modification to the design. So what we have done is we packaged the conducting dipole sandwiched between two FR4 layers. So actual dipole, just like the before, but there's another FR4 layer to change its characteristics. This is the cross dipole, resistive cross dipole. And we change these parameters because now we want to absorb more frequencies, reduce transmission over more frequencies. All this is resonance device. It does absorb and transmit very well in this band, but you can design it to absorb and transmit outside the band as well. So these are the curves of transmission is 2.1 magnitude and reflection is 1.1 magnitude. Not just normal incidence, but various oblique incidence as well. Transverse electric 0, the same as transverse magnetic 0, so it's a normal incident. TE30 is transverse electric at an incident angle of 30 degrees. TE45 and then the others are S11. So what you see here is transverse electric up to 30 degrees, and up to 45 degrees. It behaves similarly. And I believe we have another plot for transverse magnetic. Transverse magnetic is a little trickier, but again, you can get absorption, less transmission, and less reflection over fairly wide range of frequencies with this kind of FSS. There's a different new name for this kind of absorbers. I forget the name, raspobers or something. So just a lot of papers now on this subject about printed wideband absorbing surfaces. I think radar absorbers, because of that they call raspobers or something. But there's a lot of work happened after this. During this time, there are not many. I can't remember any wideband thin printed absorber. Okay, now let me check my notes. So EPG. Okay, I updated this slide. It is sitting on me. Okay, this is the one you saw yesterday, day before yesterday, but I have done few updates. Partial reflecting surface we will discuss with resonant cavity antennas. We will go through EBG structures and photonic crystal slides today. Now you're talking about, I was thinking I was supposed to do that before this, but anyway, we started FSS. We done that and this. Now about artificial magnetic conductors. That's another very useful periodic structure. And okay, let's see, I will change sharing. Why do you need artificial magnetic conductors? This is a way to representing. Okay, this explains why. I remember we discussed this antenna yesterday, day before yesterday, printed monopole. So this is an antenna that I think I mentioned it is called bidirectional. It radiates upwards, it also radiates downwards. But sometimes you don't need downward radiation, right? Because you may integrate this on top of a laptop or any some device. And so there's no purpose of having downward radiation. And in fact, if you attach this to a conducting surface, the downward radiation would hit the surface and it's actually short circuited by the surface, conducting surface, and the antenna will not work. This kind of antenna. And so we want a reflector to reflect the radiation going downwards back to upwards. So for that, we can't use conducting parts. We can't use conducting material. In fact, that kind of antenna cannot be placed close and parallel to conducting parts like a screen, circuit board, hard drive, computer case, a laptop case, etc. That kind of bidirectional antennas, because they radiate into lower hemisphere very well. If such is printed on top of an electronic box like a game console or anything, radiation will be a waste. And in addition, it is short-circuited, the electric field is short-circuited due to this effect. So, if you have a wire antenna like this, you can install it on an electric conductor, wire antenna perpendicular to electric conductor. Typical example is an aerial in the car, like those old aerials. That's nearly perpendicular, there's no problem. Because this antenna, wire antenna, is polarized vertically. Remember, day before, yesterday we were talking about wire antennas and polarization. Vertical wire antenna is polarized vertically, so electric field is vertical. We have an electric conductor here, but that is not a problem because the conductor is perpendicular to electric field. However, if you have a wire antenna or strip antenna like that one in the previous slide, and place it parallel to a electric conductor like metal, because this antenna is polarized horizontally, electric field is horizontal, that electric field is short-circuited by this surface. So a wire or strip antenna cannot be placed close to and parallel to an electric conductor. Very close to it. If you want to place it, you have to place it at quarter wavelength above the conductor. Quarter wavelength above, that will not short circuit because of the impedance transformation of quarter wavelength. But also that is frequency sensitive because it's quarter wavelength at only one frequency, other frequency is not quarter wavelength. However, if you can make a magnetic conductor, it will not short circuit the electric field. In fact, it will double the electric field. The magnetic conductor doubles the incident electric field. Just like the electric conductor doubles the incident magnetic field. Like here, there is a magnetic field parallel to the electric conductor, and the reflected magnetic field is equal to incident magnetic field, equal in magnitude, equal in phase, so it doubles. And likewise here, incident electric field, reflected electric field is equal to incident electric field in magnitude and phase, so it doubles, so it's really nice. But there's one problem. There are no magnetic conductors. There are no natural magnetic conductors. You can't go to the store and buy a magnetic conductor. So you have to make an artificial magnetic conductor. So those are the artificial magnetic conductors. It's a very well known one is the one mushroom shaped one published by Sivan Piper. Uh, these are like mushrooms. These are conducting patches uh, with a vertical section on the ground plane, full ground plane. You can print this on a PCB using VRs, and that works as artificial magnetic conductor. Then there's another artificial magnetic conductor proposed by, actually demonstrated by University of California, Los Angeles, by, I think it was, I forget those. So I know I was a good friend, but I forgot his name. The major MTT group um, in UCLA, called unipolar compact mag AMC. But anyway, what you need to do, it is a 2D, it has 2D periodicity. You need this surface to have zero reflection coefficient. That is that you need the surface to reflect very well. Reflection magnitude should be 1. Reflection phase should be 0. Reflection magnitude should be 1. Reflection phase should be 0 for electric fields. Normal electric conductor like this one has a reflection magnitude of 1, like PEC, perfect electric conductor. Reflection magnitude is 1, but reflection phase is 180 degrees or pi radians. So that is opposite phase. That's why it cancel out and create a null. Here you need the surface to have a 0 reflection coefficient. So making artificial magnetic conductor to work at one frequency is not very difficult. This is one example. Uniplanar compact one from UCLA is another example. There are a lot of designs even at this time, but it's difficult to make them to operate in 2 bands. So we try to make one operating in, we wanted to make one operate in 2 bands, the Wi-Fi low band 2.4 to 2.48 gigahertz and the Wi-Fi upper band 5 gigahertz band. So we need the narrow AMC band here and wide AMC band here. So this was our design. This was not exact for those frequencies because of the they still had 2 bands with similar ratio. So this is our dual band AMC. If you compare this with uniplanar compact, there is some similarity, and we extended UCLA design by adding additional slots, and we fabricated it using laser micro machining, and tested it and published in papers. So you can find some papers. Because of the time, I will not go through the paper, but I will try to show you one of them. This one in micro and optical technology letters. I got to switch the. My PhD student Yarding Leo is the first author of this, and our collaborators who did laser micro machining. The configuration can be seen here a little bit better. So this is a unit cell of the periodic structure. And this part was from UCLA, but we added additional slots to get the other resonance. As a result, we got 2 resonances, and the other, I will leave you to go through it to find the details, because we are running a little bit behind. Okay, so if you run artificial magnetic conductors, ultra-wideband reflector surface. Now that is quite interesting. Okay, so this is about dual band antenna, right? Dual band antenna that is bidirectional. We want to make it unidirectional, so you put a dual band artificial magnetic conductor. What if you got something like ultra wideband antenna, like the one we discussed the other day? A lot of those are also bidirectional. This is the one you saw the other day. It has 2 semicircle slots. So that's also bidirectional. It radiates upwards, it radiates downwards. Sometimes you don't need the downward radiation. And sometimes it's a problem, as I said before, you cannot integrate this close to a conducting surface because it will short circuit the antenna. So you need a reflector. You need an ultra wideband reflector, something that behaves like an artificial magnetic conductor over an enormous bandwidth, ultra wide bandwidth. So doing it in one frequency is easy. Doing it in 2 frequency bands is harder. Doing it over a very wide band of frequencies is pretty hard. So this was our solution. This is a chapter, invited chapter in the book. So our chapter is making ultra-wideband antennas unidirectional, phase coherence with ultra-wideband frequency electric surface reflector. I think that gives you an idea how we're going to do it, right? So we take a bidirectional ultra-wideband antenna, fairly standard one, and then we design an ultra-wideband FSS reflector that has phase coherence. That means the reflection, it's very highly reflecting, and its reflection phase is close to 0, as close as possible. So that's the idea, and we designed it, fabricated, tested, and published in a few places. There are some publications too. And after that, this book editor invited me to write a chapter to his book. So this is now a book chapter. So this is same story. We have an antenna here, and we want to radiate only the upwards. not downwards. So this is a bidirectional antenna. Some radiation goes up, some radiation goes down. We want to block that radiation, reflect it back to upwards. And we can put a metal reflector, as I said before, at quarter lambda naught by 4 distance. That will do at one frequency. But it don't work over a very wide frequency band because this is frequency sensitive, the gap. It will work only at one frequency, will work over narrow band of frequencies, doesn't work over an ultra wide band of frequencies. So what did we do? We put a frequency selective surface, one frequency selective surface to reflect a part of the band, about half of the band, okay, with the correct reflection phase. So by the time it get here, the effective reflection phase is 0. But it won't reflect the other half. The other half goes through this FSS, and we have second FSS to reflect that back, and it comes through this first one again. By the time it reaches, counting all the path delay, etc., the effective reflection coefficient is close to 0. They never got to 0, but it's good enough. Normally, plus or minus 90 degrees is good enough. So with those two together, they reflect most of the band and the reasonable phase in this location at the level where we would put the antenna. And there are a lot of other details in this book chapter. I will only describe the most important parts. This is the first layer, FSS layer 1, unit cell for the lower band. And then this is the other FSS layer 2 for the other band. Actually, I can't remember. Yeah, this is for the lower frequencies. Sorry, this is for the upper frequencies. Higher frequencies reflect the higher frequencies, reflect the lower frequencies. Second one for lower frequencies. The first one reflects the higher frequencies. What I said before was wrong. FSS1 reflects the higher frequencies. This one. And the lower frequencies go through and reflected by FSS2. So we look at the properties, the reflection characteristics, optimize, oblique incidence performance. How does it work when the incidence is at not 0, at oblique angles? The field distribution in the near field distribution, and so on. And we measured it, we fabricated it, tested it with ridged horn antennas. Yeah, the measurement setup is not interesting. That's the FSS, fairly large, quite large number for unit cells. Oh, the other thing is actually these unit cells are not of the same size, if I remember. So that creates problems in designing. The period is normally different because they are for different bands. So you can see the horns, transmitting horn, receiving horn, to measure reflection at various angles. This is a setup to measure transmission. We don't have full ground plane, so we have to, that means it does not guarantee 0 transmission. Unlike those AMC surfaces that has a full ground plane, so there's no transmission. But in this case, we don't have full ground plane, so there could be some transmission, so we have to measure transmission as well. but transmission is very low, as you can see. This is transmission versus frequency, less than minus 10 dB, our very wide range of frequencies from about 4 gigahertz to some, these are measured up to 11 plus gigahertz. Then the fun, the most important part, we use it as a reflector for our ultra-wideband antenna. So we just put our ultra-wideband, bidirectional ultra-wideband antenna very close to this surface and tested it. This is the ultra-wideband you saw in the previous lecture. And we measured gain at different frequencies and changed the height above the FSS to find the optimal height. You don't need a lot of spacing. So measured input reflection coefficient and the predicted S11 magnitude input reflection coefficient. But this blower graph. This one is very interesting. So just the ultra-wideband antenna input reflection is this, the blue curve, broken curve, and it is well matched. You can see the S11 magnitude is less than minus 10 dB or equal to minus 10 dB. Now, if you put it on a perfect electric conductor, PEC, and measure S11, this is what you get. And this is what I said before. The electric conductor reflects with the wrong phase. So you get a lot of mismatch. That's because of that short circuit. In some frequencies, it is good, but in between, it's bad. Very bad mismatch. A lot of frequencies, the input reflection coefficient is greater than minus 10 dB. Now, with our dual layer FSS, placed again only 2 millimeter, antenna is just 2 millimeter above the surface, just like PEC. The input matching is the green solid curve. Now it is matched, well matched, better than minus 10 dB. Reflection better than minus 10 dB. All the frequencies from 5 gigahertz to 11 gigahertz. So that was the purpose, and we achieved the purpose as a reflector, ultra-wideband reflector. If you plot the beam in 2D, without the ultra-wideband reflector, this is polar coordinates theta and phi. You can see this is bidirectional antenna. There's a beam, upward beam at phi equals 90 and another beam at phi equals minus 90. So bidirectional. When you put it above the frequency, ultra-wideband reflector, you only have the upward beam. So it's unidirectional. There's a little bit of field here that is due to transmission through the reflector. It's not a perfect reflector, but you can kill that beam almost perfectly using the ultra-wideband frequency selective surface reflector. That's one advantage. Second advantage is because you are reflecting that energy back, you get better directivity. So you get like 3 dB increase in directivity when you reflect like this. And the patterns, so this is without the reflector, and this is with the ultra-wideband reflector. This is our antenna, ultra-wideband with two semispherical slots. Another way to look at the beam radiation pattern. This tall one is the bidirectional pattern without the reflector, going upwards and also going downwards. The other one are the two pattern cuts with the reflector on V plane and H plane. So you can see there's no backward, not much backward radiation due to the reflector. We also designed a 4-layer FSS, very similar to the previous one. I think we did this before. For a slot antenna, wideband, ultra-wideband slot antenna, this one has 4 layers of different frequency selective surfaces. So we divide the band into 4 different bands. Each FSS reflects part of the band, just like the previous example. This is the ultra-wideband antenna, large slot, rectangular slot antenna that is bidirectional, and we use this as a reflector to reflect. It also works, but it's more complicated because we need four PCBs, sorry, 4 layers, 4 metal layers in the PCB. And designing is very difficult as well because the periodicity is different, as you can see. Some cells are larger, unit cells are larger than other unit cells, so we can't really, there's no common unit cell for all 4 layers. So it had to be designed individually and optimized together. Okay, going back to my outlines, done AMC, ultra-wideband reflector, absorb, transmit, FCC absorb, FSS absorbers, right? Enhanced transmission to energy-saving glass. There's a couple of other. I think we take a break, right? I already missed the time. We're supposed to take the break.
Okay, so no issues there. Okay,
15 minutes. Come
yeah,
back,
we
come
have.
back in 15 minutes.
Okay, so we'll resume the next session at 12:15, and there are some, I think, query from audience. Respected Karu sir, please leave us the title of the book.
So you come back at 20 past 12,
Yes.
right? That will give 15 minutes.
Okay.
20 past 12.
Okay. Okay.
That
Thank
is 5:45 my time. Okay.
you. Okay.
See you then.
Okay.